Hello everyone, and thank you for joining me for Handmade Hero. Today we are going to be doing lighting, and we pretty much got lighting working last weekend in our sort of test way that we wanted to make it work. And so this weekend, really what we're doing is we're trying to push the lighting quality forward, right? Like we basically got like a rudimentary version of it working in a little CPU testbed. Eventually we will port it to the GPU to run on there directly. But right now we're using the CPU. And the reason we're using the CPU is because we can visualize and debug it a lot easier on there than we can if it's running on the GPU. So even though we could have implemented this on the GPU, it's just much nicer and just a lot more pleasant to work on the CPU. It's sad that we're still in that situation, but that's just kind of the way it is. GPUs being highly non-standard as it is, and also often not having proper debugging capabilities built into them, which is another aspect of it. But so if you take a look at the game as it is running at the moment, one of the things you can note here, I'll go ahead and turn, oops, that's not good. We don't want to look at the profile. If I turn on the lighting to show reflectors, and we can look at different aspects of the lighting solution here, you can see that if I just look at the reflectors, you can kind of see if I move the light around, you can see that we have light propagating kind of around the scene. And there's some weird flickery sorts of stuff that happen, and we're not super sure. Those could just be bugs in there, like that right there. They could be actual bugs that we're kind of go start looking for now as we try to solidify things and get a good quality solution. They could also not be technically bugs. They could be what are effectively bugs but aren't really technically bugs. And what I mean by that is with something like lighting transport, especially when you're simulating multiple bounces, we've been really sloppy so far. We're just kind of hacking some stuff in there in terms of the lighting transport equations. It's easy to get into a situation where you could make a solution that can bounce more light than it receives, right? And if you create a solution that can bounce more light than it receives, then what you create is a sort of an infinite feedback loop, right? So the number of times that you iterate the lighting, you can actually just get brighter and brighter and brighter, right? So that's another thing that we haven't done yet, is like ensure that we conserve lighting when it's bounced around. In fact, I'm pretty sure we aren't doing it right now. So things like that, where things get infinitely bright, could be straight up bugs, meaning like somebody typed, well, somebody would be me, but there was a typo or an incorrect part of the algorithm, so it's actually just not functioning properly. That can be one thing. But it can also be the case that you may have typed in the algorithm properly and it's doing what you expected it to do. The problem is just the algorithm is not conservative. And then, therefore, you can end up with feedback loops like that. Just if the game happens to get into the right state with the geometry, then there you go, right? But either way, you can sort of see, like I said, that lighting is sort of working here. So we're in a position to start focusing on whether we're doing it well and whether the quality is there and so on. Now, if I turn to show visibility, you can also see the computation occurring here for ambient occlusion, which is a part of the lighting computation. This is just viewing just that part of it. Excuse me. And this is an important thing to understand. This algorithm that we sort of started off using, which probably isn't the one that we'll use in the end, now that we've got things set up and working, we probably can fuss around with it a little more. But now that we've got this working, you can sort of see that it doesn't really do a very good job of doing any sort of shadowing that we might really care about, right? So what you can sort of see here is, the ambient occlusion may take out a little bit of what you don't want to see in terms of light propagating to places it shouldn't propagate, just based on like the fact that these things are in like a corner or something like that. And that is nice. That does add one of the main things that we do want to the image. So it is good that we have that. There's no question about that. But it's worth noting that that ambient occlusion, while nice and while it is important to the look and can be used for that, You can see right there. You see that weird flashiness? Yeah. It'll be interesting to see what that is. But anyway, it's also not really going to do some of the stuff that we need to do with shadowing. And it's the only shadowing that we have in there right now. So we can forego better shadowing, but it's worth noting what it does and doesn't do. And so right now, one of the things that the shadowing does not do is if you look at how the game is currently lighting this area back here, well, you know, that should be pretty dark. Because if you turn off the reflectors, you can kind of see that there's just these big walls in the way. And if I go back here, you can see that this area is really just pretty much fine in terms of brightness, right? There just isn't a lot of darkening happening back there. And while it's okay to leave it that way, like, you know, it's certainly not a problem to have that be the case, because as we start to smooth out the lighting solution, you know, it could be that the look of the game is just fine that way either way. But the real issue there is just that, you know, if we want a solution that does a little bit better at preventing light from bleeding around edges, that's not going to do it for us, right? That's not gonna take care of it. Especially because, you know, as I kind of come behind here, you can sort of see that, you know, this is getting lit almost, you know, not quite, because it's getting darkened by these by default, but it's getting lit almost as if this wall were not here. And that doesn't really make much sense. So, and again, that's because we're not really doing any work right now to detect the real... we're not really doing much to say if a light source is on one side of an occluder, it can't propagate light to the other side of the occluder, right? We're kind of just doing ambient occlusion, which isn't really the same thing in that case, right? So yeah, so it's a little bit confusing, and it's certainly, like I said, something that we kind of have to think about how much we want to do in terms of accuracy and how much we don't, you know, really necessarily care about it or just want to go with something that's going to produce a pleasant look or whatever. But the first things first, so first things first, we want to kind of work on our lighting solution a little bit here to try and get to something a little bit more stable. And one of the things you can see if we just show the visibility is that for the most part, the flashing, the super bright flashing doesn't really happen here. So, you know, as far as we can tell from looking at the two parts of the lighting solution, there are some oddities. So for example, you can see like right in here, how things darken kind of dramatically in a way that doesn't necessarily make a whole lot of sense in terms of visibility, because it's like, okay, if I'm just moving between here and here, you can kind of see that there must be some kind of bug or bad feedback. It could just be bad feedback, but you can see how these darken considerably more just right along here, which doesn't seem to make a whole lot of sense. Again, it could be because the ambient occlusion algorithm is pretty ghetto. It's basically like just doing two passes of propagating, or it might be three at this point, of propagating the shadow information of how much each occluder shadows every other occluder. So, you know, hard to say about that. But with that in mind, it's just, well, okay, so, you know, given this circumstance, does that really seem logical enough? And again, like I said, I don't know if it does. But either way, if we take a look at the difference between how much effect that's having and how much effect we're actually getting when we see these super bright flashes, it just doesn't seem like the super bright flashes are coming from the ambient occlusion pass. Now, what we can do as well, presumably anyway, and let's just verify that. So if I come along here and I move along, and let me try to find a place where I can see those super bright flashes. For some reason, I'm not getting the super bright ones. We were getting really bright ones before. There we go. So you can kind of see that super bright flash happening there, for example. If we go and disable the part, oh, I guess I didn't, yeah, I don't know why I felt compelled to restart. We have the live code reloading since we're on the CPU side, so that's pretty easy. But if I come through and I take the lighting part that was just computing the ambient occlusion, which, you know, here is the part that sets up the lighting. I should have commented this. Here's the ambient occlusion part. If I was to take the ambient occlusion part and just get rid of it entirely, so that the visibility is always set to 1, right? So here is the, you know, visibility always set to 1. If the visibility is always set to 1, then in theory I should be able to see whether I still get the sort of the lighting issue there. So if I go to the show reflectors, right, here's the visibility. So the visibility is now not changing in any way. And so if I assume that the visibility is taken out of the equation entirely, do I still, and you can see I still get those bright flashes. So we know that the ambient occlusion is not where the problem lies in terms of the like sort of flickery weirdness. And so what I'd like to do is just take a second to see what's going on there, because that does seem a little bit iffy. So another thing is just to take a look at what degree this has to do with feedback. The other thing I can do is I can sort of simplify this down by saying, let's just temporarily disable any iteration on the lighting as well. And so then, oh, and you know what, I should also just put us into the mode permanently. In fact, you know what I could do? I can just use config for this. So if I want to, in here, what I could do is say, well, all right, let's look at the reflectors. Let's not look at the visibility. Let's only do one iteration of the lighting solution. And that will give me what happens when I only do one pass. And so what you can kind of see here with the one pass of the lighting is that my sort of assumption appears to be correct. It appears that the initial lighting solution is relatively stable, does not have that sort of nasty propagation problem. And so it would appear that either we have a bug in the way that we propagate information once it's already been propagated once. So, you know, something where we're writing to a variable in a way that's inconsistent. So if you loop through or something, you get nasty artifacts in that variable. Either that's the case, or what I was suggesting before when I was talking about the problems with having the sort of the non-conservation of light potentially leading to really bad feedback loops. We don't know, that could also be an issue. It's unclear. What I will say is that taking a look at this, if we were to eliminate, and I guess what I could also do here is add, in addition to having that iterator controlled, we could do it here. So we could do global renderer occlusion iteration count, and that could be something that we can put in here. So if we did, I guess it's 2 iterations, I think. Is that correct? How many there normally are? Yeah. So if we do 2 iterations on the lighting pass, the ambient occlusion pass, rather, then what we should be able to see is what happens if we combine just the stable basic lighting solution with the ambient occlusion. So here's the visibility. You can see the darkening sort of happening there. And you can see the lighting like so, right? And so this is the combination of the 2 of them. And it's sort of interesting. Again, I'm just taking a look to see what it ends up looking like. So in here, if I was to say, like, okay, let's take this and let's switch to, in the config file, turning off ambient occlusion. Oh, and I guess I got to... if I go in here and turn on the ambient occlusion. So the ambient occlusion definitely does darken things down quite a bit. You know, whether or not it darkens them down in a way that we find useful is another sort of question. But it's kind of interesting to look at anyway. One thing that I am kind of interested in too is how we're going to sample these lights at the end of the day, because right now we're just sort of reassigning them to the quads that they came from. Which doesn't smooth out the lighting in any way. So, because obviously we're not going to want the lighting to be blocky like that. We're going to want the lighting to be interpolated. And so that'll be an interesting problem as well, kind of as we go. But that's sort of a separate issue. So, yeah, but looking at that, you know, it does seem like that's actually still an improvement, though. Like, for example, the stairs don't get that lighting because they're sort of blocked and out of the way. So it does seem kind of like it does a reasonable job of improving the solution somewhat, but it's not that appreciably different, right? Like, I don't think, at least at the moment, if you were to show me these two, I'd be like, well, it doesn't really seem to add much, right? It doesn't seem to add much in terms of what I would suspect we would see when we finally do the good sampling of it. It doesn't seem to really provide all that much that you would bother running it, right? Like, it's not, it just doesn't seem like it sort of has enough going for it, the ambient occlusion part of it. So I'm more tempted to say, like, you know, if we were looking at that part of the algorithm, I think we probably want to do something a little bit fancier there, or try to make that be a little bit more about shadowing and a little bit less about ambient occlusion, because ambient occlusion, again, it's not really that interesting in a lot of cases. It's kind of not really what you want in terms of figuring out where things should be darker or lighter for light sources that are not ubiquitous. You know, if you just have a skylight that's coming in from the top, then ambient occlusion maybe is your friend. But if you have a situation where you want to be able to move lights around in some way, like I am moving them around right now, ambient occlusion doesn't really capture that the properties of that very well, because the ambient occlusion, sort of by definition, is really only talking about the degree to which a surface can see the general outside sort of world, which isn't, that's really not what that is, right? Okay, so what we want to do now is again, start to look at this lighting a little bit more. What I want to do is take a look briefly at that flashing stuff, and just see if we've turned occlusion off here. If I turn on viewing of reflectors, and we can sort of verify there is no flashing when I'm just viewing reflectors by itself. If I go in here and say I crank up the lighting to 2 passes, we should see a little bit of a problem, but not as much of a problem as 3, I would assume. And it actually looks pretty stable at 2 passes. But if I crank it to 3 passes, yeah. And, you know, you can kind of almost just see right off the bat, just the fact that it's getting brighter kind of overall kind of indicates that the solution is kind of tending to go a little bit nuts, right? And so presumably what would happen is if I kept cranking that iteration number out, we would just end up with the whole scene being white. And that is basically what we see. So I think what we're going to have to do here is, and 3 seems like a good sweet spot for seeing the really nasty flashing too, so that's good, so we'll just leave it there. So I think in terms of sort of convecting that light around, I want to start to be a little bit more careful about this. We'll leave ambient occlusion for now, and we'll leave it turned off, so we won't fuss with that. But we'll take a look at the compute lighting pass, and let's just go through this and think about what we're doing here and why we're doing it, and whether or not it makes very much sense, right? All right. So I think the first thing to think about here is the sort of directionalness of the bouncing of the light, I guess. Because we sort of have just an inherent problem to think about, and here's what that problem looks like in my mind, anyway. Where is Milton? That is not Milton. Why do we have so many things open? What's going on? Do I have more? No, I guess I have the standard number of things open. All right. So today is day what? 40. Oops. Whoa. So it looks like the fix definitely did not work. Whatever it is. It's really weird. We have no idea what causes that problem. I need to just find a way to debug it sometime. It's the only problem that we have at the moment with any of the tools, really. We haven't run into pretty much anything. Let's relaunch that. All right. So day. It's weird. The tablet tracking also seems to be a little bit weird in this one now. Day. Huh. Well, who knows? You know what I should also do? I should check. So is that actually just because our drawing has gotten too large? That's the other thing that I wonder. So if I was to say, have Milton open up a different drawing. So if I just said new Milton canvas, right? So if I then said, okay, open Milton canvas, no, Blackboard, open. No, so it just seemed like it was some kind of a temporary thing, I guess. I don't know. It's so cool that Milton can undo after you load. All right, well, either way. So let's talk about light conservation here. So fundamentally speaking, the problem that we have is we have an emitter. And so the emitter is sending light out into the environment, and then we have reflectors, right? And technically, at this point, we are not doing anything to sort of understand the fact that lighting, the amount of light is conserved. So if you imagine that what we're trying to do is say, okay, we have an emitter, and this emitter outputs, say, you know, X photons per second, then what we could say is that we know that it's going to, you know, in any given frame, if we're running at, say, 60 frames a second or 30 frames a second, we know that if it does X photons per second, then it's going to do X over 30 photons per frame, right? So we would, or 60 or whatever, right? Whatever, however many frames per second we're doing, we're going to divide the number of photons that this thing shoots out. So whatever our emitter's strength is, that's going to be the case. When this emission comes out and it hits one of these reflectors, the photons are either going to be bounced out to other reflectors or bounced out to the eye. I mean, some will be absorbed, right? But wherever the viewer is, let's say the viewer is here, right? Here's our little eyeball. Then when a photon comes in here, it's either going to come out and hit the eye and we're going to see it, or it's going to come over here and hit this guy, right, or something, But a photon can't do both, right? Light does a lot of weird things, but that's not one of them. And so however many photons come out of the emitter, if we're saying that a photon went over to some other reflector in the scene, it can't also come out and show up for this reflector. So what that means is the color of this reflector as viewed to the eye, right? And the color of this reflector as viewed from this other reflector, the brightness has to add up, right? It can't put 100% of the photons that come at it, send them over to this reflector, and also send 100% of the photons over to the eye, right? It's just not possible. And so by the same token, we end up with the problem that when we have two reflectors pointing at each other, which is exactly what we have here, if photons are sent from this reflector to this reflector, then if those same photons were sent back, right, then this reflector would be black. It would be completely dark, right? If all the photons hit this reflector, it sent them all to this one, and it sent them all back, right, then sent them to the eye, this one would be black. But that's not what our algorithm is simulating at all right now. What our algorithm is actually simulating is that if all the photons come in here, we consider this reflector to basically be however bright it is when viewed from the eye or from this reflector. Now, technically, that's not necessarily wrong in the sense that a perfectly diffuse surface does reflect light equally in all directions. But the question is, how much light does it reflect in all directions? And we have to take into account the fact that when it reflects light in all directions, it has to divide the amount of light it reflected by the angle out of which it's radiating that light. Because if it doesn't, then again, you're just multiplying the amount of light in the scene dramatically. Right? So right now we have absolutely no, we have essentially no way of sort of keeping that process under check, I don't think. So that's problem number one. Problem number two is that we are resampling the emitters every time as well. So basically we push light into the scene with the emitters and they are outputting the light. And then in theory, when we then convect the light around, so when we're then saying let's do secondary bounces, technically we shouldn't be looking at these emitters anymore, right? Because they already put all the light into the scene that they're going to put into the scene. They are not receiving any bounce lighting, so that's just kind of erroneous at that point. So at the moment, in terms of a radiosity solution, this is typically what you call solutions, lighting solutions that are like this, where they bounce light around and try to reach a steady state. This is not very good, specifically because it's got all of these sort of leakage problems in it like that. And we're seeing the results of that just from the standpoint of our lighting solution tends to sort of explode. It tends to just go out to bright white rather than having each iteration converge towards a smooth answer, right? So what we want to do, if we imagine that the total amount of light in the scene should be, you know, some specific value, whatever this is. This is like the correct total light. This is how much light. If we imagine looking at our iterations of this algorithm over time, what we want is something, you know, we don't care how it approaches. We don't care if we're biased or unbiased really at this point. What we want to know is just that no matter what happens, like however this happens, we just want to know that we're converging either from too bright to the right amount, from too dark to the right amount, or just stochastic to the right amount. But what our algorithm is actually set up to do right now is like this, right? It's just set up to just keep increasing the light in the scene ad infinitum. And so the more iterations you run, you don't get closer to any kind of good solution to the light transport. You just are just adding light arbitrarily to the scene, and you don't actually improve the solution at all, right? So what I would say is the first thing that I think we want to do is we want to start thinking about the emitters as being a first pass only thing. So I'm thinking that probably what we want to do is like overwrite the emissions value sort of with 0 or something like this after, or we want some way of essentially saying once we've done the first outpouring of light from the emitters, we don't want those emitters to emit light anymore, right? That's just that's just a tenet of the solution. And we furthermore could sort of say that, you know, we could even think of it as basically being a photon bouncing. We could sort of say that at the beginning you load up a bunch of photons, and again I'm just kind of making this up as I go, but you could say we load up a bunch of photons on the emitters and then we bounce them out and we store how many photons the surface is going to keep for its own illumination versus how many it's going to send out into the environment. We could imagine that as actually being like a quantity that we track, right? And I don't really know if that's a good idea, but that's certainly an idea, and we can do it. So the question there is just how would we start to model something like this? And, you know, it's a little confusing because if you think about it, it's like, well, something doesn't get brighter or darker based on how many observers there are to it, right? But it is uniformly radiating the light out from its surface, and that means that because it's doing that, it is always darker than it would have been if it was a specular surface and you were viewing it from the right angle, because a diffuse surface that radiates light in all directions, but by necessity must have divided the amount of light that it was radiating by that sort of total angle, right? And so all I'm trying to say there is we need a solution that will have the property that if it is a diffuse surface, the total amount of light that it can possibly transfer to things in the environment must be consistent. And that's actually somewhat tricky for us to do. The reason that it's tricky for us to do is because of the way that we have set up this this system, and you know, this is just an artifact really of the sort of the approximation that we're using. If we don't have shadowing, which we don't really, then if you think about an emitter and two reflectors, right, we are not looking at the fact, and I guess I should actually say, let's suppose these are all reflectors. So the emitter is here, and I hit, you know, this emitter's got light, it shines onto this reflector. So this reflector is now radiating light out into the environment, and it's irradiating however much light it received, it's radiating that back out in all directions, right? So if it was taking in 100 photons or something, then, you know, maybe 20 of them go out this way, and 20 of them go out this way, and 20 go out this way, and 20 go out this way, and 20 go out that way, right? So, but it adds up to 100 still, or less than 100 if some got absorbed. So the problem is the way that we're computing how the light bounces around is we're saying, well, let's take each pair of these and see how much of the solid angle of the world this one takes up. Like, how much can this one see? And when we do that, we end up looking and seeing that we, you know, can see this occluder quite a bit, this reflector quite a bit from both here and here. We don't take into account that this part right here is shadowed for this you know, part of this reflector. So really, it can't collect nearly as much light as this one can from this emitter, because part of it's being blocked. And since we aren't taking that into account, we will naturally increase the amount of light that's in the scene kind of ad infinitum if we're not careful, specifically because of that shadowing that we're not taking into account. So that's a pretty big problem there. And like I said, there's a couple ways we could approach it. One way we could approach it is by just doing photon distribution in some kind of more sane fashion. And so I guess what I might propose is the problem that we're going to have with this is that until we get to the end of the until we go through everybody and do that lighting computation, what we don't actually know is how much of this sort of thing occurred, right? Because we have literally no computations for shadows in there, and even if we add some, they're going to be pretty approximate. So we're definitely not going to end up with a good solution there. But what we could do, since we're sort of overestimating the contributions, there is one thing that we do know, which is we know the total emittance, right? However we want to measure it, photons, lux, whatever, like we, however we want to, lumens, however we want to sort of put caps or specify our lighting, or even just an arbitrary value, handmades, whatever it is, we know that how much we started with. Because our emitters, at the beginning, before anything else happens, we know how many of them there were and how bright they were supposed to be. So we have some value we can use to say this is the total brightness that should get distributed through the scene, full stop, right? And so if we know that piece of information, then one interesting aspect of it is we could say that at the end of every lighting pass, we do not expect to have any more than that light in the scene. So we could track the total light as a sum and then normalize to that at the end, right? Now, the problem with that approach is that that's going to be easy to do on the CPU, but I suspect it's relatively tough to do on the GPU. Maybe not. You could use a hierarchical approach to sum the light in that case. But you can kind of see why it's not maybe the best idea because of its global nature. Essentially, the problem with it is, if I imagine how that would be done here, you could see in this compute lighting thing, we could just have something that was like, oh yeah, you just say the total light is some value, and then we come through here and we sum it up, and at the end we divide by that value, and we're done, right? So inside here we'd just say like, total light plus equals, right? And then we just want to make sure the total light matches up at the end. And that's it. So we can do something like that, but then again, you can see when you're in a straight line path like this, using accumulators for a global accumulator is easy because you just put it in line like that. But when you move out to a parallelized version of the algorithm, you have a problem, which is that at the end of it, you have to gather up that sum somehow, and that can be pretty tricky on a GPU. Even though it wouldn't be tricky on a parallelized version on the CPU. Oh, excuse me. GPUs, at least, but unless you're using like CUDA or something, GPUs are actually really bad at that. If you're just using like DirectX or OpenGL, they don't have a lot of good ways of saying, here's the concept of a thread. Let's have every thread increment some variable that's how much it did of thing X, and then we'll sum those at the end. Again, it's just because the shader stuff wasn't really initially set up for it. So you end up like having to get pretty far down the line with extensions and whatevers, or even just like go to something like CUDA to get to the point where you have basic threading primitives that you might want, such as value per thread, or thread local storage, whatever you want to call it. Which makes that kind of solution, which makes this solution to this problem trivial. But again, I don't really know that we're going to have access to it in Shader Model 3. So anyway, so we could do something like that. However, even that doesn't necessarily solve our problem, because it doesn't necessarily mean that the light is sane in terms of how it bounces around in areas. Because then what you still might get is a circumstance where you've got 2 reflectors or 3 reflectors or something like this, and emittance that comes in here just bounces around it here really a lot and jacks the total lighting in this area substantially for no real reason, just because it is over contributing. Its contribution is overvalued because you're only doing that sort of total lighting. So what we would rather do, I think, if we can, is figure out some way of keeping the total radiance from something, the total sort of output radiance from something, to be fairer in general when it's being computed, such that when you see it from 2 places and I got my light from you, we just sort of have a difference between that emitted light and the reflected light to the eye or something, right? We need some way of keeping these values sort of more stable through the iteration process, if that makes sense. And unfortunately, I'm not really sure. This is the part where probably what I would do if I was programming on my own is I would want to go read some of the radiosity literature, the original radiosity literature, just to find out how they tend to structure their solvers so that the light that bounces around is summed up in a fair, is summed up in a fair model, right? But I'm not really sure. I'm not really sure how they do that, right? I'm not sure how they traditionally set that up. It's good. It's going to have to be something fairly careful in terms of how you account for the light. And I don't know if the approach that they tended to take was, let's make sure we calculate the lighting transfer accurately so that we don't have this problem at all, or if they were like, no, we try to make something that converges on the solution and we can have sloppy calculations for how the light is transferred and we still expect it to come back to something reasonable, right? So yeah, that's what I would normally do, but I don't think that doesn't tend to work particularly well on the stream, so I think I'm going to have to just kind of hack it through myself, if that makes sense. But I would say that, that's what I would advise doing. So, in terms of this being an educational stream, what I would say is that if you are looking at a problem like this and you're not sure about it, and there is a bunch of literature on it, which in this case, like I said, this is just called a radiosity problem in computer graphics. It's well studied. It's not the kind of thing that you're going to have to go digging for extremely esoteric papers to read about. There's a lot of papers about it. Probably what I would do is go try to read the radiosity literature a bit and just familiarize myself with what has already been done in the area so that I can kind of, know what the general techniques might be and see if any of them are going to be, worthwhile here. But if I have to puzzle through it myself, then I guess what it comes down to is I'm a little bit stuck on this sort of problem of not knowing about the occlusion process. I'm just not sure how you deal with that. Because without some notion of the total amount of light that you are expecting to have, I'm just not sure how you deal with that. And furthermore, I guess, if you don't deal with that properly, you're always going to have the thing I talked about with the over-contributing. So I'm not sure. So you may just need a total light value. There may really be... there may really be no straightforward way to make sure that you don't over-contribute if you don't have proper shadowing. Yeah. it sort of seems like you just have to have an overall exposure value that's like, here's how much light got transferred, which we know is going to be wrong because we're not occluding properly. And then we just have to, dump it down from there. And I don't know if there's really any other way to do it. Because without a conservative way of transferring the light, you're always going to have some overflow. And if you have some overflow, if you don't have any way to measure the overflow, I don't see what you could really do. Yeah. I can't think of any other solution. If you want inaccurate lighting transfer, it seems like you have to be summated. Now, I guess what I could say is that the ambient occlusion might be enough to make it so that you never have to worry about it transferring too much if you do the rest of it correctly. Because thinking through what happens with the ambient occlusion, if anything, overshadows things. So the visibility value that we compute with the ambient occlusion is going to knock it down based on the total amount of occlusion there could have been. And it should overcompensate. So in theory, this value here is going to be reflected. The fact that it's taking up part of the solid angle here is going to be reflected. I guess what we don't know, however, is that that's really true for lights, because the light could be coming from a totally different angle. And if the light's coming from a different angle, all bets are off. Yeah, I'm not sure. So let's think about this from, I guess, just from the perspective of if I let myself use the sort of total lighting approach, let's just see what happens. So what I want to know here is how much total light, sort of have a value that's like the total amount of light that should be spread around. And so, what we're sort of doing at the moment is we have these lighting elements, and some of this information is dynamic and some of it's static. So we should sort of start to maybe segregate that. So here's the static information. And here's the dynamic information at the moment. All right, so I believe transparency and radius, those are not dynamic, right? They don't change. The rest of this stuff, I guess, reflect color. So reflect color is currently not dynamic either. There we go. Should probably be on this side to avoid going underneath my head. So if we take a look at what's going on there with the PNTRFC there, that top part, those are the values that are actually set by the game engine sort of irrevocably, and they just remain the same the entire time. So those are not values that iterate around. Then we've got sort of the front emit and back emit values. The front emit and back emit values, we're not doing back emission yet. We should for sprite cards, obviously. And then we've got the accumulated color, the visibility, and the shadow. So the way this is working at the moment is that the shadow value and the visibility value are used in the ambient occlusion pass, right? So these are really and technically the shadow value, this is like a transient value. We don't really use the shadow value except as like an accumulator. Like it's really just a QMC for ambient occlusion, right? And so what happens is we store our results into that shadow value. It could just be like a temporary array that was right in just this loop. It doesn't need to persist. So that's a transient value, and the same is true of a QMC, right? A QMC at the moment is not used as the actual like permanent value. It's used as something that gets transferred eventually. So you can kind of see like in here, right? When we're computing the light source information, we grab out of the source, this light color is the front emit C, and we store back to the accumulator. Then at the end, we take the front emit color, and that's when we take that accumulation into account, right? So in here, we could also say that this part is transient, right? Another way to write this, I suppose, would be like this, but I don't know. I'm going to keep them with their sections, and maybe I'll put it at the end. So, so basically what we want to do is we want to focus on how we would go about approaching the light conservation problem. So what you can see here is we've got this front emit C, we've got the emission value and the color.rgb. The emission value is just telling how bright this thing emits, right? And so that tells us the total emission. Only our lights are going to have front emit C set to something at the beginning, and off we go. Now, one of the interesting things about ref C, which is the reflected color, is we should never allow a surface to reflect 100% of the light that it receives. Why shouldn't we allow a surface to reflect 100% of the light it receives? A, because there is no such surface, I don't think, in the world. I don't think there's such a thing as a perfect reflected surface. So what we want to probably recognize is the fact that the reflected color from a surface has to be somewhat less than the light coming in on all three channels. So red, green, and blue light that comes in, it has to be reflected out at less than what hit it, only perhaps very slightly. The reason for that is if you think about trying to do any kind of accurate lighting solution, I don't know why we're still running the game, by the way. What is this? OpenGL error encountered? What's the error? Failed to compile GLSL shader. Yeah, that's no good. Cannot apply dot operator to an array. What? Did I accidentally touch something in the OpenGL code? What was that? I do not know what it was complaining about there. To see if that happens again, or if that's just OpenGL being weird. Anyway, back to what I was saying. So the problem is that if we actually look at what would happen if we allowed 100% light transmission, is that if you have an emitter that emits even a single photon, right? Here's one photon, and these are 100% reflective surfaces, you can get a situation where this photon just bounces back and forth forever, right? It literally creates an impossible scenario where there's no way to ever get the light to transfer properly, right? Because there has to be, in order for there to be a stable lighting solution that you can end up with, there has to be a way that all light eventually goes somewhere. You can't have it that light bounces around forever and expect to have any kind of converging solution, because if the light can bounce around forever in the scene, then there is no solution, right? There is no actual solution to what the color is of each individual surface. So typically speaking, we want to make sure for our lighting situation that our reflectance should be something like this. So when people specify RGB colors, they can use the full range if they want to, but our actual interpretation of what that's going to mean in terms of when we reflect light around, we're going to assume that what that actually means is that the reflected light is less than the total light that came in. And we'll assume that our surfaces can get pretty reflective, but just not all the way reflective. 0.95 or 0.9, 90% of the light, 95% of the light can be reflected out, but not 100%, right? And so we'll just assume that that's the case. Now, so moving on from there, when we take a look at this emission situation, right, we now have reflectance that we know would eventually converge, and we have an emission color that we set. When we go into the sort of this iteration thing, if I want to have some idea of the total amount of light, what I can do is I can just have that value be stored in here somewhere. So I could do something like total light or total light levels or something like this. So that we come here and we track how much light is going to be emitted at the outset of it. What I can say is that the total light levels are going to be the sum of all of the emitters that we have. And I could say initial total light level even, just to say which one that was. So I can keep a total of how much emitted light we started with, right? And one thing I'm not 100% sure about is the emissions values, how we're arranging those. I'm not really sure how that value is supposed to be interpreted, but we know how much total initial light there is in the scene by looking at this initial total light level, right? That's sort of our value that we could understand. So then when we come through here in the secondary loop and we do our lighting computation, we're going to transfer a certain amount of light every time, right? So we're going to take an amount of light and we're going to transfer it. And that transfer, however much light got transferred, we could say that we want it to sum up to whatever the initial total light level was, or something similar, right? So on each iteration, we could say total light transfer. And here we could say, all right, every time we do an accumulation, we will say the total light transfer gets that value added to it. So then at the end, we know how much total light got transferred on each of our channels. And we now are in a position to potentially do something about it if we wanted to, right? Now, since we don't super care that much about the reflectance values, we kind of just want to know more about how much light we did total. I'm wondering if this kind of, though, does need to be sort of thought about just as a single power value, right? Like a photon power value. Because we don't really want to normalize our channels separately, so it's a little confusing, right? Because what we really want to do is say, all right, when we come through here, we've got the specular light level, the diffuse light level. What we want to do is sort of say, well, how much light were we actually putting out here? We really want it to be more like this value here that we're tracking. And I guess I can do that pretty easily. So if I do something like this, because these are these are this is just a series of scalars that have been blown out so that it can multiply the reflected color later. Actually, that's not quite true. So it's actually this part in here that I want. Because I don't really want to multiply by the light color yet. So one of the interesting things here is that that multiplication actually could have been done at the end as well, because the light color is the light color regardless. So if you take a look at what's happening here, I guess it's if you want to change the specular color and the diffuse color separately to have more of a control over the light source, then it makes some sense. So I sort of see why we did it, but still. So what I really want to do here is just have some like this distance fall off times diffuse coefficient times cosine angle. What I really want here is diffuse contrib or something like that. So that's the diffuse contribution. The specular contribution, it looks like can be done exactly the same way. We're not using this yet, so we don't really have to care about this path, but I guess we'll sort of leave it in nominally. So if I have both the specular and the diffuse contributions, then what I can do is say that the that sort of accumulate value here is just going to record that information. So the accumulate is going to be the diffuse contrib plus the specular contrib. And that's how much, and I suppose to keep this naming reasonable, we'll say the accumulated contribution. So once we know the accumulated contribution, we can do the total light transfer is plus the accum contrib. We can assume that since we're modulating by the visibility, we'll do that as well, right? So that modulated visibility there, that gives us the total light transfer. And now we know how much light we transferred versus how much light we should have. So what I can do there is say, here's the initial total light level. And what we'll do is we'll just use that as a scalar value. So we'll say the initial total light level is going to be whatever the vert 0 emission was, and we add that together, right? So now we kind of know how much total light we're putting out into the scene in a sort of hacky way. And we should be able to then say, well, if we know the total transfer and we know the total light level, we can correct for the wrongness of the transfer, right? So what we could say is like the correction for the light amount is going to be the total light transfer is how much we got, right? And we want the total light level. I should say the initial light level. What was it called? What was it called? I thought I called it like initial light level or something like that. Initial total light level. So we can compute a correction factor that's like, we should have had this much light total in the scene. We ended up transferring this much light. Let's just keep those two consistent, right? So what we can do is say that correction factor applies to the total amount of light that we end up with. And I guess the problem here is that again, that transference, though, we're trying to keep the total amount of light constant across everything. So in theory, what we would do here, I guess, is just say that we want to keep the total light level constant for each go around. And so presumably this correction would keep it so that we've sent that amount of light around. But that doesn't really help us with the second part of the problem, which is the fact that each iteration will convect that much light. But in theory, right, as long as we account for the number of iterations we're doing by just by just saying each step is an averaging step, that should be okay, right? So in other words, the correction could also factor in the number of iterations we're going to do. So, you know, we add in the correction factor and also the total number of iterations. We divide by the total number of iterations. Seems reasonable? So essentially what we're saying there is like, okay, so each time we add lighting in, we're going to add as much lighting as there was total. But we want to make sure that we only add that amount of light in the end. Meaning, so we're going to have however many lighting steps we do. If we do 3 lighting steps, we want to make sure that we add the correct amount of light on each step. But we also want to make sure that we are averaging each of those steps together and not adding the entire amount of light every time, right? So that should give us the answer there. However, the problem with this is the front emit C values. Again, for the initial emitters, we need those to be zeroed out. So the initial emitter needs to not contribute light anymore after the first time that it's shot light out into the world, right? Because at that point, it has done its job of putting the light into the world. It's not supposed to, it's not supposed to put light out into the world again on the next pass. So what we really want probably here is, rather than summing the accumulation, maybe this just wants to be setting the accumulation. So this is how much light you actually got, right? We push the light out and we bounce it around. And so if we do that, then we wouldn't need this, I think. Right? So again, that's really pretty hand-wavy of me. Like, nothing in there makes a whole lot of sense. I'm just kind of, again, going for something to see if we can sorry. I'm just trying to like puzzle it through a little bit to see if I can get to something that seems more reasonable in terms of convergence. So specular contrib, specular C times cosine ref angle there. There we go. All right. Cosine, this is actually diffuse inner. All right. So yeah, the convergence properties there, I'm starting to get a little bit more of a handle on, I think, what should be happening here. Because yeah, the iterations, I'm not really entirely sure how those emitters should work in that way. It's a little bit tough to say, but I'm interested to see what we get. So we'll find out. So anyway, let's take a look at how this is working, just so we can kind of get some idea of what's going on here. So if I go into, well, I guess I can't do that. Let's set a breakpoint on the routine lighting test. Looks like it's not open. So if I come through here and let me compile in debug mode as well. Here we go. Just make sure this is still working. Yeah. So if I stop in here and I start looping through, let's see what the initial total light level value comes out to be, because I have no idea. So 6 is the total light level. I assume that's because we have 6 emitters outputting at 1, right? Excuse me. And again, that's not really, we probably need to improve how we're describing that, because it's like, okay, how big are the emitters? How do we want the light values to be? Is the light value the total amount, when we say emission, is that the total amount over the entire surface? Or is that per unit surface area? Blah, blah, blah. So we haven't really talked about really how that's going to be specified yet either, which is a bit of a problem. But we're skipping over the ambient occlusion, so this should not do anything. When we go to compute the lighting transfer here, so as we go through, we look to see what the light distances are for these things, diffuse center, and so on. In this case, this is a non-contributing light source. One of the things that I guess I didn't do is I don't take into account the emission here, which is probably bad. This is just how much of the light could have transferred, but we didn't take into account how much of an actual transfer it was based on the light color, right? And that's sort of like, there's sort of this notion of how much light that surface had to contribute at that point. So that, now that I think about it, that's an open question. So the only way we could really handle that part properly is we'd have to store how much light we bounced to each surface as well, right? Like how much light we gave to that surface. And so I do wonder, it seems like that's just gonna, like trying to be conservative about the light like this is just gonna sort of drag us down into like having to track more and more and more values. So here's a question for you. Can we just rely on the averaging part of it? Like, let's say we didn't try to do the sort of nuts thing of trying to actually track the total light and keeping it correct. What happens if we force the emission to not be additive and instead we let it bounce? What do we get? I'm curious to know. Oh, and I need to build in. So you still get very flickery results there. Whether you add, right, or not. So it gets like slightly brighter, but it's surprisingly not that different, which is somewhat interesting. So now let's see if I do put a correction in here. I'm curious to know what happens if I like make the iteration count relevant. And so you still get a really, you just get a really surprisingly temperamental solution. So yeah, I'm really confused about that. So I don't know, maybe we do really need to track the total light transfer, but now, you know, like when I was looking at that, I'm like, well, okay, if we actually do want to track the total light transfer, we have to actually remember how much light could have been coming from the particular source in question. Because, so each one of those needs an F32 that's like, how many photons do I have to transfer, potentially, right? Because a surface that has not had any photons hit it can't give you any photons. And so you'd be massively over calculating how much light was potentially transferred on each pass if you don't store that value. So that does seem kind of nasty. I don't know how to get around that. Let's think about this for a second. Is there something else I could be doing here that would make that work? I can't say I can really think of anything. Well, I mean, I guess what I should do is, I think probably the best policy is just to try ridiculous stuff until we see where we're at, and then we can always simplify later, right? Seems reasonable enough. So if I was to actually say, like, if I was to do something ridiculous like photons to send and photons received, what I could say is like, all right, you know, we come through here and we say that this element photons to send equals the emission, the photons received equals 0, and the initial total light level is, you know, the summation of the photons to send. And initial total light level we could just say photon count, total photon count. So that just tells us some made up value that's like, here's how many photons we have to send around, and off we go. So then when we come through here and do the lighting computation, we can say total photons sent. And when we come through, we'll say, all right, the source, we'll just go here, photons sent. So we'll say the photon sent equals whatever this particular source is, photons to send are, times the two contribution values, right? So whichever, you know, however much light could potentially transfer times the photon sent is the total photon sent. Then at the end, what we could say is, all right, the total photons that we sent are going to be however many photons we sent times the visibility here. And that's a value we can actually store, right? So I guess what I should say is, instead of that, when we loop over the dest here, well, no, I guess I still need that value. Inside the destination here, in addition to the accumulation color that we're accumulating there, I'm going to take the photons sent, or rather the photons received, and I'm going to assume that however many photons were sent in this pass, in fact, I guess I should name that the other way around. This is the photons received, right? So I'm going to sum up all of the photons that were received. At the end, I'll store that, and the total photons received will look like this. So that gets me how many photons I received, and how many photons were received in general. So at the end, when we do this, now we know we can introduce the correction. We can say that the total photons received, we want to sort of correct those photon values by the total photons that there are. So that's our correction factor. So when we come through here and we say, let's take our destination, excuse me, when we want to compute these next values, we'll say the photons received. We're going to clear that out for the next pass, and the photons to send are going to be however many we received. So we can always send however many we ended up receiving. So then we're just kind of convecting it around. Now, the emit color, so we're going to ignore all that stuff now, and we're just going to draw the photons received. So in the copy lighting out, when we do this stuff here, I'm going to say if show lighting visibility, else if lighting show photons. What I'm going to do is in here say that the photons to send are going to be what we show. Then what I can do is in the config, we'll have a thing for that, which is show photons. And now we can see what the photon transmittance values are for everything. Oh my. How did we get a blue in there? I suppose that this is probably because the photons to send value needs to be divided by the total number of photons. Let's try that one more time. All right. So here we can see this sort of nominal photon transference idea. It still looks busted because how are we getting blue? I don't know if blue, I'm not sure how the blue is happening there. But like, yeah, because in theory, the front emit should not ever be able to be greater than 0 now. I'm sorry, greater than 1. Let's do an assertion. All right. So that does look bad. So our algorithm is definitely not right yet because there should be no chance for any element to have anywhere near the number of photons that are the total number of photons in the scene, right? So let's go ahead and recheck that. So We come through here, we set the total photons received to be 0. We loop through all of our sources, and we say however many photons the source had to send, we're going to multiply. Well, in fact, and we don't really care about this, right? Whatever this number is, it doesn't matter. We're going to get a photons received number. Summed over all the sources is how many we received. We're then going to say that the destination the photons received is going to be however many that was times our visibility, which in this case should be 1. That should not be really reducing it at all. We're then going to say that the total number we received gets incremented by that amount, and that's checked outside. When we finish the iteration across all light transfer pairs, we then say, okay, the correction value is going to be however many photons there were total. We want to take the total number of photons received and divide by that. So this is going to be 6, right? And this is going to be some other numbers. Let's actually look in there. Okay. And so like this number is 40.85, whatever. That's the total amount of transfer that occurred. We only want the total number to be at 6. So what we're going to do is we're going to take 6 over that value or whatever, right? Oops. Guess I can just look at the actual value. And we're going to correct everyone by that. Oh, hi. How about I actually didn't? That's pretty good. How about I do all this work to construct a coefficient for correction, and then I never bother to like multiply anything by it at all? How does that sound? Pretty good, right? All right, so now we're out of the business of overestimating the light there. Hopefully now when I run, we have something more sane. Okay. So now we can kind of see this looks more correct, right? So it seems a little more sane. However, you'll notice the flickering is still awful. And so I don't know. One thing that I'm a little bit interested to know at this point is, do we have another bug in here that's actually what causes that flickering in some way? I don't think so, because when we don't do multiple iterations, we don't see it. So presume, like for example, if I go into the config here and I said the iteration count was 1 on the photon transfer, there it is, I'm assuming we'd no longer get the flicker. And we more or less don't. So there's that. One thing that I am a little interested to know, so if I was to say that the lighting iteration count was 3, like we were doing before, and in fact, let's just say it was 6. Let's just go nuts. So we're just going to iterate the lighting like lots of times, right? So it really just seems kind of nonsensical to me. And I don't know if maybe that's just, like I said, maybe we've got some other kind of bug. But in this case here, we've got, I'm going to go ahead and just assume, like here we've got a situation where we know we're keeping this total photon number even, and just the distribution of it is just absurd after 6 iterations, right? It seems to be like kind of arbitrary where the photons ended up, which is a little bit weird to me. Maybe that's what should happen, I don't know, but it seems odd. And if I look at the photons to send, which is the only value we're actually viewing at this point, it sure seems like it's sanely capped. So I don't know. I don't think I really understand what's going on. It's a little bit troubling. So, you know, let me go ahead and change the iteration count down to 1. So there's 1 iteration. And then if I change it, you know, and can I still do this? Yeah. So yeah, if we're just taking a look at this situation here where we're zooming around, if I change the iteration count to 2, you know, now I get this weird concentration of light on the middle guy there, but why would that be the place where the photons get concentrated? Is that just because there's so much more transfer for things that are close together or something? And I don't really know. Oops. How come I can't, oh, right, because I'm playing back input. I'm like, how come I can't rotate the camera? I'm like, that's because I'm playing back input. So the other interesting thing about this is I almost want to take the hero out for the moment and just be able to move the light around. So what I might say is, can we just go to world mode and when we add player, what if I just don't give it any actual pieces? Actually don't want that to be running. There we go. So if I run it now, I should just have just the light source to move around, right? And it looks like it's got a health meter as well. I'm not sure how we have that. I'm not sure I remember how we said that somebody had health. But there must be some way. It's got to know somehow init hit points. So now I'm just moving the light, right? And it certainly does seem, at least from this, because now I can go into the config and say, let's increase the lighting iteration count. It certainly does seem like from that having those things stacked together is a problem, or at least, you know, it exacerbates the problems with our lighting transfer, because you don't get I guess it's because they're so close together. Maybe because they can sort of transfer light at too high of a. It might just be like a nasty singularity in how we were doing our lighting. Maybe we just have a bug in the distance computation there. where if things are too close together, they can transfer light to each other extremely easily, and they just kind of go super critical at that point. That does seem plausible anyway. So you can kind of see that a lot of that jitteriness goes away when you don't have those stacked sprites all kind of hopping up and down like they were. So I think that suggests to me that I just need to fix the transfer function. Maybe the transfer function is most of the problem there. I say. Let's take a look. At how we would want to go about this. So if I look at the front emit color here, and I assume that we're just setting it, so if I was to do the summation that we were doing before, right, here's that summation. So what we can sort of see is it's actually totally smooth if you just have occluders that are spaced pretty far apart. So that's pretty important information, I guess. Because here we are doing like a lot of lighting iterations. Let's see what happens if I crank it up further. So basically what we find is, yeah, you do get the light, sort of the too much light transfer problem, but you don't get the flickering. So that's very important information. So we need to like deal with that. I'm interested to know if we take what happens if we multiply the photon correction here. I can't imagine it's a good idea, but let's just see. It does seem like it's a good idea. All right, so here, this is kind of nice. So our photon correction does do a good job of keeping the lighting relatively consistent across multiple iterations. So if I crank up the number of iterations here, it definitely keeps it a lot more sane. It's still not sane enough. Like, we're still doing something stupid. I'm not sure what. But it still is increasing the total amount of light it looks like. Oh, because this is a plus equals though. So that's actually not that unusual. If we were to do a straight equals, I think we'd be very dark because currently we don't have any exposure control or anything like this. So that's probably not super plausible at the end of the day. But I think we're kind of getting there. All right, so I think what we've learned here is that we need to take our distance fall off and we need to fix it so that it doesn't have a bad behavior when things interpenetrate or get very close to each other. I think that's been a big problem for us. So we need to fix that. And then the other thing that we need to do is then we need to figure out whether or not or how we're going to try to keep a lid on the amount of lighting that gets put out into the scene. it's possible that we don't really need to do it. Like, it's possible that we can cheese it, because it seems like, anyway, once we get down, once we get rid of that bad sort of singular behavior when things get too close together, it looks like just simply keeping the light relatively under control is enough. So there's 8 iterations. Here's 16. And that's pretty good. So I guess I would say, it seems like just keeping it so that we only take, just keeping it so that we are essentially just using an averaging process for the color seems sufficient to me. So that's good. Let me see here. All right. So yeah, I think iteration-wise, that kind of solves that problem for me. So I think at this point, all we really need to do, I don't think we'll have to do the photon control there. So I think all we really need to do is keep things from going super critical, and we'll be okay. Because again, we're not trying to compute any kind of exact lighting solution here, obviously. So it seems like we should be okay. So let's get rid of those entirely. All right, and so now we should be able to just have, so now we've got some pretty stable light in there, which is good, and we can build on that and make it better, right? So really what we need to do now is we need to just go in there and figure out why are we getting such a bad behavior, and I'm assuming it's from the distance fall off, but we'll see. Why are we getting such a bad behavior when there is a hero added to the mix? So let's go ahead and add first back in the body pieces and see. So there you can see some of that flashing happening, right? And also what we can sort of see here is too that, these things are bright, completely white essentially. And so I do wonder too, right? Like if we only iterated once, are they white already? Yeah, they are. Right, so even the first bounce of light makes them be that bright. So that's kind of interesting. All right. So let's take a look at what we're actually computing here for our fall off. That's not the right file. So if we're going to do here in our compute lighting, if we're going to do the fall off, here's our distance fall off. We have 1 over the square of the light distance. That just seems wrong because we want the distance fall off to be, so you know what? Probably this was just wrong the whole time. So if you think about what happens, in fact, you know what, I can probably do this using one of those saucy graphing things. So let's see, graph square root of x. So you can see the function that we're looking at here. I don't know if I can zoom in. I just want I don't know if I can tell it, I just want the 1-to-1 range. do we? How do I... Ah, there we go. That's what I'm looking for. So if I do that, so you can see this function here. So for our square root of x, I don't know if I can change, am I allowed to change this here? Not really. All right. We're doing 1 over whatever the square root of x is, right? So we're graphing 1 over the square root of x. Unfortunately, it doesn't save our graphing thing. That's all right. It's not the end of the world. So you can see that underneath 1 here, you get this sort of super ridiculous spike. And I think that's exactly what we were seeing. What we wanted was a distance fall-off factor that basically said that the fall-off, presumably at the light source, so if you're standing right at the light source, right? There we go. So at the light source, looks like we lost Milton again. There we go. So at the light source, that value should presumably be 1, meaning there's no fall off. And far away, it should approach 0. Now, it will never be exactly 0, because inverse square law, it'll just keep getting lower and lower and lower, but it'll never quite hit 0. But what we actually have, at the light source, the distance is going to be 0, right? And so the square root of 0 is not 1. So we have 1 over the square root of 0. It should be 1 at the light source. It's actually going to be going off into infinity, right? Sorry, going down, well, it's going to be, the square root's going down to infinity, which is going to make our value, is going to go down to 0, which is going to make our value shoot off into infinity. So actually what we want to do is say we want 1 plus the 1 plus x, right? Because that way our value trends up towards 1 and hits 1, not infinity, at 0, right? And we did that correctly because we were working off of the paper in here. We did reciprocal square root, right? But when I typed it in here, I'm not sure why. I just wasn't thinking, so I didn't do it that way. But that's what we actually wanted. So that value has always been wrong. And it would explain where that singularity was coming from. So now that we have it correct, actually you can already see that now we're okay. Right? So we had just had a rogue term in there, and that was what was creating that nasty flickering, because that was injecting arbitrarily like close to infinite powers of light into our lighting solution, and hey, big surprise, our lighting solution didn't like that very much. So let's try cranking it up to 8 iterations and see if we're still stable. We are. So I'm going to consider that a good victory. All right, so that was just like just a typo in there. So it turns out that is what our flickering problem was. And then now I think we're pretty good in terms of lighting solutions. Just the basic transfer working, it seems pretty reasonable, right? I am interested to know if we can change the color. I don't remember myself what we were doing here with color. When we add a standard room and we put the pieces in here, so we can, all right. So what we can do is we could say for color, we could take this here and do something where we actually change the color if it's a wall. So we could do something like have it be a very red sort of wall. And what I'm interested to see here, right, is I'd like to see if we can get some light bleeding happening at some point, which it doesn't really look like we're getting very much of, which isn't good, right? What I'd like to see is, because in theory, if this light is bouncing around in the way that we think it should, then when you get in a situation like this, you should get some red contribution coming in here, right? And one way we could exaggerate that, well, I guess I'm going to just say, one way we could exaggerate that is if we just said that everything was either perfectly red or perfectly white. And if we go through and look at what we get there, let's see, do we get any color bleeding? And, you know, we get a little, right? You can sort of see that we are getting a little bit of color bleeding, but it's very minor. And I don't know if that's really what we should be expecting here or not, but maybe seems a little bit less than it should, I guess would be my only thought there. So the other thing we could do too, though, is I guess we can leave ourselves with a ambient occlusion pass as well here, just for fun. But yeah, you can just see that you don't really seem to be getting very much at the moment. You don't seem to be getting very much of it. And again, it's hard to say if that's accurate or not. That's always the problem with lighting things like this. But I mean, I guess I would say you do get a little bit, right? It's just not as much as I probably would have wanted, but you do get a little bit of that color bleed. Because, you know, what you should see is these big red reflectors, you should see more of a red tinge in here, and you really don't see much. And so I wonder, I feel like that's the next thing to start looking at in terms, because ignoring ambient occlusion, which we need to sort of start working on separately, tomorrow I think what I'd like to do is figure out why we're not getting enough of a transfer there. And what happens if I start with just one iteration, right? I get none, because I shouldn't be able to get any color bleed there. With 2 iterations, I should have gotten some, but I don't seem to. I mean, you know, if I did, I got extraordinarily little. And I feel like it should have picked up some from that contributor because it is close. But it just doesn't seem to really have done so. And if it's not picking it up on that second bounce, it probably won't pick it up ever. I don't know. It does look like as you go through more iterations, maybe it got a little bit, but I'm not sure. So let's go ahead. To the Q&A. It's supposed to be square and not square root. It might supposed to be. Let me see if I put that wrong in there. Oh, yeah. Sorry about that. I just graphed it wrong. So there you can see it passing through one as it should. right? And if I get rid of that, oops, you can see how 1 over x squared has this nasty problem of just shooting off as we get down below 1, you get this nasty shooting off into infinity, right? And it makes sense, right? Because as you get lower and lower, 0.1 squared is 0.001 or whatever, right? You keep getting higher and higher as this value goes below 1. So you never really want this value to go below 1. And there's 2 ways you can do that. You can either square, we could do, this is, I have to actually go see how we actually want to do this. This is one way to do it, right? Which is we can do 1 plus the square because as that goes to 0, so it goes up from there, or we can do the square of 1 plus the value. And I guess I'm not sure which one of those is more correct. I think this one is probably the more correct. How many iterations are we doing here? It's a little bit slow. So yeah. Question, now we don't need to do a global path to normalize light. Yeah, because, so the thing is that, again, this is an approximate lighting solution. So we're not doing, we're not trying to do anything that's actually going to produce a physically correct lighting result. So if I can, my preference is definitely to make it so that we don't have to do a pass to normalize light. That would be my preference. So because we can do an averaging process, which is what I'm doing now, and it appears to keep the lighting under control, I would say we definitely don't want to do the lighting, to have to enforce a lighting pre-pass. I mean a lighting post-pass to correct. Masfielda, is it useful to convert the surface color from RGB to YUV in these equations, as in using Y to modulate light contribution somehow? I don't think so, because generally speaking, you want to know the spectrum of light that you're, like, RGB is actually the right space to do lighting computations in, if you're not going to go full pull and actually do spectrum information, right? But you definitely don't want to convert to something that doesn't tell you which of your colors is the color where the intensity is, because you're trying to bounce around colored light specifically. So I don't think there's any bonus to doing it in YUV. There is a bonus to doing it in spectral, some way that stores more spectrum information, because some things need to know whether, say, a yellow light is actually a yellow wavelength light or a combination of red and green wavelength lights. So, if you're doing really high-end stuff, you may want more spectrum information than just 3 samples, R, G, and B, because that doesn't tell you very much about the incoming light, really. But I don't think YUV helps in any particular way. Could be wrong about that, but I don't think so. Do you know how much a CPU gather costs compared to a load from a linear memory read? So are you talking about, for example, the gather call, the gather instruction in AVX 512? Is that what you're referring to? And how much it costs to do to have the CPU do the gather, as opposed to if the CPU just pulls in a cache line? Is that what we're talking about? I'm not sure what you mean. Oh, okay, I see. You're saying GPU gather. So again, what kind of GPU gather are you talking about? And I am tired, it's true. So by the way, if I only do one bounce, I should not see any light on the backs of those things, right? So what's kind of cool is when you actually have iterative lighting, it's kind of neat that you get some light now from those. It's not really quite right yet because we're not doing very good shadowing or any shadowing. But convecting light around is just good. It tends to make a nice smoother image. Caleb, spectral lighting is something I never heard of before. Can you point out some good resources on the topic? I don't know. So you might be able to search through it this way. The other thing I wonder is, does physically based rendering, the book, have it in there? It's a pretty standard reference on these sorts of topics, and I don't know if it actually has that in there or not. So it's a little hard to tell just from here, but you know, my hope would be that this would have that in it. this book has a lot of, is a pretty good basic reference for like, I need to learn how physically based rendering works. I hope that it has some stuff on Spectrum, but I don't know for sure. The eighth mage says, in the CPU, it's much more efficient to read a cache line using mmload and not use the gather commands. Is the same true of the GPU? Not really. So I guess what I would say is the tricky thing about GPUs is they have much more specific memory swizzling kind of stuff that they do, especially because you got these sort of weird access pattern things they try to do where they've, you can imagine how textures, they, rather than keeping like a line of pixels in a texture, that's not very good for cache locality because they tend to fetch from textures in little square areas, right, at a time. So they tend to use like a Z pattern or some kind of swizzle pattern for the memory accesses, and stuff like that is not always known to you unless you've talked to the actual GPU vendors to find out what goes on in that respect. So to the best of my knowledge, you cannot assume that like what is a gather on the CPU is going to be a gather on the GPU and vice versa. Obviously, doing things that fetch through the memory subsystem in a coherent way are always probably going to be faster than ones that don't, but what is a coherent read on the GPU is not obvious, right? Sorry, if I don't know if that's responsive to your question. But I guess that's the thing that I would say is that GPUs have highly optimized memory subsystems that don't look like CPU memory subsystems it's not exact, right? It's not like a GPU's memory subsystem is exactly the same as a CPU in all respects, where it's just like cache lines and they're linear and it's mapped directly and there's only one way of mapping it and blah, 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 right? So I think that it's difficult, especially if you don't have intimate knowledge of the hardware. I think it's difficult necessarily to predict what the actual cache behavior of the GPU is going to be at all, actually, because you don't have a lot of insight into how things are being stored on the GPU in the first place. And again, even if something appears to be linear from how it's described or from your perspective, it is not necessarily linear on the GPU itself. And the way in which the GPU's window into its own memory causes that memory to be organized can be quite a bit different than what you would expect. So again, I would just lean on the texture example of a way that gather doesn't work the way you would expect. So, you think of a texture as being a linearly mapped texture, and that's how you submit it to the GPU and whatever else happens. But in reality, the GPU wants that texture to be swizzled, right? So the GPU wants to reorganize the texture so that texture is laid out in a different pattern, right? And so when we think about how that works, then you have to think about, well, why does it need to put it into a particular pattern? Well, it needs to put it into a particular pattern because of the way its memory accesses are going to work, right? And so when you think about whether something is a gather, that makes it difficult because since you don't know how the graphics card may be swizzling the stuff into its memory, you don't necessarily know what is a gather and what isn't a gather, right? So if you need to do a bilinear filter on something, or you need to do texture mapping a small area, and you're like, well, how coherent is this texture mapping going to be? I think it's pretty hard to really know without collecting some statistics or talking to a GPU vendor really what's going on. On a CPU, you kind of know to a certain extent that the addresses are mapped linearly, things are stored the way you said that they were stored because you wrote them and now you're reading them. You know the size of the cache lines, you know the alignment of the cache lines, and all that stuff is very well documented and understood. And that's really just not the case on GPUs. I mean, I don't know, for example, the GPU of this machine, I have no idea how it's storing things. I have no idea what its cache line size is. I have no idea how big its cache is. I have no information about any of that stuff. We could try to find it out, but I don't even know how it reserves parts of things that are cached. There's all sorts of things, like there's a texture cache, typically, or cache unit that pulls things in to like texture from. I have no idea on any particular card like what that looks like. And once in a while, you can take a specific card and ask a bunch of questions and get down to like, oh, here's exactly how this thing does a bunch of stuff. And maybe you care enough on a particular platform, like say it's a PlayStation 4 or something. Maybe you care enough to find all that stuff out because it's a fixed platform and you want to optimize specifically for it. But it's really just difficult to sort of figure out that stuff on a broader scale. And yeah, you can't really swizzle textures yourself, really. So my understanding on that, and again, this could be dated, but my understanding on that is that the problem with swizzling textures is that every card wants textures swizzled differently. So the way this works is there was a standard swizzle format, I believe, that was introduced for DirectX, maybe, or some kind of standard swizzle thing. There's like a nominal attempt at it. And I believe all cards have to accept data swizzled in that format, but that may not be the format that's fastest for the card. So what actually happens is every card has a different memory subsystem typically, and that memory subsystem is based on what type of memory and memory bus and stuff they've got set up. And so my understanding, and this is fuzzy because again, I don't work with this stuff very much, is that NVIDIA cards, for the most part, at least the higher end ones, I believe, have memory subsystems that can do the swizzle in the memory subsystem. So they can actually accept textures that don't have to be swizzled in a particular swizzle format because they have the ability to swizzle the memory controller, I think. Do not quote me on this. Again, this is way out of my area of expertise. AMD cards, however, because they are often designed to target the lower end of the market, they have specific swizzle patterns that the memory controller can do, and you have to be swizzled in one of those formats. You can't pick an arbitrary swizzle format and expect it to work. It has to be the one that's whatever that memory controller does, and it's different depending on the card SKU. So my recollection is that it's actually kind of a nightmare in that right now you really would need something like a query call that says, hey card, what's the algorithm for swizzling your thing? And somehow that would have to be represented back to you. And then you would have to swizzle into that format. So it's not the case that there's just one swizzle format and you could just store all your textures pre-swizzled in that format and upload them without having to go through a swizzle. That is not the case as far as I know. You pretty much have to have it be swizzled to the card's format, and only the card can really do that, and there is no way to query it. However, I also was under the understanding that NVIDIA had some kind of stuff on there that allowed you to upload flat textures or swizzled in whatever format you want textures, and it could adapt. I thought there was something to that effect where the memory controller could swizzle the addresses in that way. But that's just my vague understanding, and I could be very wrong about that. Is Handmade Con 3 still at the start of 2018? I have not. I don't know that there's going to be a Handmade Con 2018. I'm very much not sure what's going to be happening in terms of conferences, unless somebody else is hosting conferences. I know there was some talk of people wanted to do one in Europe or something like that. So I'm not sure, but I have not put anything out about that, certainly. Brian asks, C-Tray improvement, would you be so kind as to give a suggestion of how you tackle saving the day number? Do you prefer temp files? Just keep it simple like how you read settings.ctray? Should I look at how you save state like in ctime? I can try to tackle an alternative this week, for I do need to become more confident in reading and writing to files. So, I mean, I would say that it probably doesn't matter very much how it's done. But yeah, since there's a settings file already, I would say probably just rewrite the settings file and put the day number in there. I don't really remember what the format of the settings file is in C-Tray because it's been a long time since I've looked at that. But yeah, it looks like you could just stick the day number down at the bottom, right? And then when you just read and write this file, so you read it in, and every time you increment the day number, you just save it back out again, right? Yeah, I mean, I think that's a reason. I don't know that making it in any file is a very good idea necessarily. It's not necessarily a bad idea since C-Tray is kind of only a Windows program anyway. There's no, there's hardly any platform non-specific part of it. Almost all of it is like talking to Windows to get those transparent overlays to appear. So it's not like there's any concern about it having to be cross-platform or anything like that. So if you prefer it to be in any file, yeah, that's totally fine as well. So I would say that's fine. I don't really think it needs to be changed from that, right? So what you've got in there now seems reasonable to me. I haven't tried it, obviously, but assuming that works okay, it should be fine. Is it possible to mode change monitor frequency nowadays? So I always try to get my game loop to run at 60 hertz. Yes and no. So if you have one of those fancy monitors for gaming that has like G-Sync or one of those things in, then yes, you can set it to whatever refresh rate you want, really. If you just have a regular monitor, then no. Regular monitors typically have a refresh rate that is, sort of prescribed ahead of time. Like, it's got some set of refresh rates it can do. And I don't think you can just pick an arbitrary one. If it doesn't support 60 hertz, you can't set it to 60 hertz, right? Now, most monitors these days would support 60 hertz. So I would suspect that if your goal is to just set the loop to run at 60 hertz, most of the time you probably could get that mode. That's not going to be super unusual, I don't think. If, however, you wanted your game to run at 45 hertz all the time, that's the one where you're in trouble, right? Running at 45 hertz all the time will work just fine on a G-Sync, but it's not gonna fly on a standard monitor. Probably doesn't have a mode that supports 45 hertz update. So, and I believe that's mostly just that. It's really just the the controller on the monitor. To the best of my knowledge, there's no such thing really as a LCD refresh rate per se. As far as I know, LCDs are more or less only about a maximum rate. Like, you can only change them at a certain maximum frequency, but there's not like a, oh, I built this LCD circuit and it can only do 60 hertz. So I'm pretty sure most of the time that limitation of it only having certain refresh rates is because the controller that's on the monitor only recognizes those rates, and not because you couldn't have had the rate be arbitrary, which is what I think G-Sync monitors typically are. G-Sync monitors are just a regular monitor that just happens to have the controller replaced with one that doesn't arbitrarily say you can only have these refresh rates. CJ question from Brian. As an exercise, I would like to investigate the cost of just bringing the overlays to the top and checking first if the overlays need to be brought forward. What should I look for? Should I profile the calls? Should I run it continuously to see if I get error cases? I realize this may not be the best thing to do as an example, but it was something I struggled with. I would say that the problem is not a performance problem. So the reason I recommended checking first is not because of performance. What I was concerned about is that whenever you change the Z order of the windows on the screen, you run the risk of triggering things in Windows that may produce unwanted results. So for example, you may end up bringing the taskbar to the front. You may end up causing an OpenGL window to lose its ability to do its VSync. You may end up causing, who knows what, right? And so mostly what I was concerned about there was not poking Windows in a bad way. I don't know that there's really a significant performance difference in either case. I don't even know whether Windows is smart enough. It might be that Windows is smart enough to know to just not do any of those things during those calls. But that was really the part that I was concerned about. I was concerned about the side effects that might occur from constantly calling those functions, not the performance. So that is why I thought it was safer to only change it if it actually needed to be changed, and not just constantly just spam Windows with bring to front. All right. Oops, I did not mean to close that. I meant to close that. Let's try that one more time. What is happening? There we go. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along the series at home, you can always pre-order the game on handmadehero.org. And it comes with a source code so you can follow along at home. We also have a forum site you go to if you want to ask questions, a Patreon page you can use if you want to support our video series, a schedule bot that tweets the schedule at you if you want to catch us live, which, as you can see, is going to be in just 21 short hours from now, and an episode guide you can go to if you want to catch up on old elements of the series. We will be back here tomorrow, same time, same place, if you'd like to see us try to push that lighting. Now that we've got some of those bugs out, we can try to get some higher quality in, which will be nice as well. Hope to see you back here for that. Until then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.